So we are happy to have today Rafael Pass from Oneway, who will tell us about Kolmogorov complexity.
Yeah, so thank you so much. It's a pleasure being here. So as we heard, this will be a talk about Kolmogorov complexity and cryptography, and in particular connection between the two. I'm coming to this from the side of cryptography, but we're going to spend a lot of time discussing this. And the whole goal will be to actually show there is an intimate connection between these two fields. In fact, in some sense, kind of the central question these two fields turn out to be actually the same. And this is joint, based on several joint works of my student, Young Lever, who is actually also here visiting for me. So, as I said, let's start off with cryptography, and I'm going to start off by just trying to summarize what's happening in cryptography for the last 2,000 years or so. So we're going to go over the first 2,000 years very fast. The last 2,000 years basically qualified as what I call the dark ages of cryptography. How did it work in the dark ages? Well, basically, cryptography wasn't really a science. In fact, it wasn't a science at all. It was really an art. And the way things proceeded were the following. We had someone inventing a scheme for, let's say, communicating securely with others. We're going to refer to that person as an artist because it was an art to invent these things. Not very different from painting. In fact, several similar people did painting and invented these things. So we had an artist invented a scheme. Maybe this artist was actually pretty good at mathematics, and he would argue that known attacks, type of attacks we know for today, fail against this scheme. So people have used schemes that before, they've been attacked, and we will argue that, okay, what we know today doesn't work. And at that point, we will deploy it, often in very critical situations, typically military situations. And of course, when we apply this, we use something in mission critical situations, eventually someone's going to break it, and that's what happened. And when it was broken, then we went back to this guy, or in fact, somebody else offered, and said, you know, we have an issue here, can we fix it? And then they will either patch it, or just say, this whole approach is dead, let's move on to something else. And that's how cryptography proceeded for the last 2,000 years. We had this type of cat and mouse game. So, the age of enlightenment came a lot later to cryptography. We had to wait until 1976, and this work by Diffie and Hellman, who said, hey guys, we cannot continue going on and on like this. Let's try to instead see if we can build a real science around this. Actually, this whole idea was back to earlier. Claude Shannon already tried to build a science of cryptography, but that turned out to be very limited approach. And Diffie and Hellman had a better, different approach that turned out to be more fruitful. So what they did was to say, let us try to first figure out what is the minimal thing we need for secure cryptography. What is a minimal object? They didn't prove that this was minimal, they just came up with an object and said, this seems to be minimal. Okay? And maybe this is also sufficient for some things. So they introduced this notion called a one-way function. Okay? It's a very visionary word. So what is a one-way function? A one-way function is a function that's easy to compute, but hard to invert. So if I give you a random x, you can compute f of x very fast. But given f of x, it should be hard to recover what x is. And the most canonical example of such a thing is multiplication. Multiplying numbers is very easy. Even if they give you huge numbers, our computer can multiply them very, very fast. In fact, we can multiply pretty big numbers by hand also, right? We teach kids to do it in school, and even that algorithm works pretty well. So we can take pretty big numbers and multiply them, no problem at all. But if I give you the product of two large primes, and I ask you to find the two primes, we don't know how to do this. In fact, this is sometimes an occupying mathematician, also for thousands of years. Right? How can we, given the product of two primes, find the two prime factors? So this is actually kind of, it's a very nice example of a conjectured one-way function. We don't know that this is a one-way function. This is a belief we have. So we believe that it's even, we know it's easy to multiply, but we believe that it's hard to, given the product, to break it apart. So if you have said, look, this seems to be kind of intuitive what we want for cryptography. We want something that's easy one direction, it should be easy to encrypt, but it should be hard for an attacker to take it apart. Now, when you look at this looks very different from encrypting messages, actually. So it's not clear. There's a big leap of faith here why this could be, actually. It seems like, yeah, maybe you need something like this, but is this necessary? Turns out, it turns out, as I'll argue very shortly, that the revision turned out to be completely right. And in the last 4 decades or so, it turned out that actually one functions are both sufficient and necessary. But before we proceed, let me actually give a formal definition of one function using computer science notation. I don't know how familiar you are with probabilistic polynomial time and polynomial algorithms. That's we don't. We don't. Okay, so let me go over this formal definition slowly. Okay, so a function f is a one-way function if it's number one homomorphic time computed.
Before that, 0, 1 to the power of star.
Okay, 0, 1 star we're defining this one function over bit strings, arbitrarily bit strings. So 0, 1 star just means
finite strings.
Finite strings over 0, 0, 1. Finite bit strings. So any finite bit string is a finite bit string. Okay. You can define them also infinite, but no. So we're defining it for finite bit strings, finite bit strings. Number one, we're required to be polynomial time computable. Polynomial time is what computer scientists, what does it mean to be something efficient? It's very, subjective saying, it's faster this computer, faster that. So in order to get like a nice theory of efficiency, in computer science, we say efficient is something that can be computed on your favorite computing language, let's say Python. We often define it as a Turing machine, but something can be computed in polynomial time. And so that means that the number of steps that is required to compute it is polynomial in the input length. So you have like an n bit string is input, 2 n bit strings is input, how fast can you multiply, what you can do easily n squared. So that we say is efficient. Now clearly, if something takes n through 100 steps to do, that's not efficient, really in practice. But in order to have a well-defined theory, we're going to stick to this thing. Okay? Typically, it just so happens that magically things can be done in n to 100 or n to 10. They can also be done in n squared. So they actually are. So this is somewhat religious. That's why we use polynomial time as a notion of efficiency. But that's notion of efficiency that's been established. Efficiency, just for simplicity. Everything I will say here later on, the polynomials are going to be very small in that section. But just to define it formally, polynomial time is efficiency. And so, number one, efficient computing, polynomial time computing. Number two, we're required to be hard to reverse. Okay, so what does it mean for something to be hard to reverse? And for who? What does it mean that no human can invert this? Again, we don't want to define what humans are. We're going to just say, I'm going to consider us all as being algorithms that can run in polynomial time. And maybe we can also toss randomness. We can be probabilistic polynomial time algorithms. Okay. So attackers will be considered computer programs that can run in polynomial time. Exponential time, look, if you can run an exponential time, you can try all possibilities, and then there is no hope to get 20 functions because easily you can flip invert. The whole idea is to say, you can essentially not do much with an exponential time, and for concreteness, we can take polynomial time as also as efficient for attacker. So we say it's easy to be done in polynomial time this direction, but no PPTs are probabilistic polynomial time algorithm is able to invert it with even small probability. So for every PPT, we require the existence of a negligible function. What negligible means here is not that important. I can tell you what it is now, but it's a function that's very small. Think of it as 2 to the minus n. Okay. Formally, we define negligible as being smaller than the inverse to any polynomial. So if you take the input length to be sufficiently big, the probability goes down very fast. Okay. So this is what has become kind of called the standard definition of a one function. Okay, and here, so what we're now saying is every such package should fail with high probability. There's actually, it's quite subtle how to define this, because probability over what? And it's important that the way you define it is to say, for example, a random string x of length n, then I compute the function on the string, then I give it to the attacker. So attacker, he knows I give it 1 to n here means I give him so he knows how long the string is, so he knows what he needs to find out. And I give him y, and I'm asking him, please find me some x of length n such that f of x equals y. So can you find something in the primitive set of f of x? And we require this to happen with very small probability. So this is today what is the golden standard to finish the one function.
How do you calculate the probability of the attacker to succeed?
Well, first of all, I cannot compute it exactly, but if you give me an attacker on my function, I can just run it many times on samples. Right? I don't care about computing it, really. What I want to prove is that there is nobody who can do it except with very small probability. Every attacker should fail. You cannot even do it with tiny probability. Like this, it's important here for applications of one functions that we require an attacker to fail even with, you should not be able to invert this even probably to 1%. Because if you have an encryption scheme that somebody can actually find what the key is with 1% probability, that's pretty bad, right? I wouldn't be very happy to say, look, you send me an email and 1% probability that everybody can read what I got here, not great. That's what I'm sending. We'll later on discuss this probability. Turns out that you can also define a weak also function that says that nobody can do better than 99%. And it turns out that these two notions you can go from one to another. There's something called Hardness of application. We'll be back to that later. Okay, but this is the definition. And so what has been shown in the last decades or so, starting in 83. So I guess it is 4 decades now. Turns out that their vision from 76 was completely right. It's crazy. One-way functions turn out to be sufficient and necessary for most of the keys primitives using cryptography today on the internet. Okay. So what do I mean by sufficient and necessary? Let's pick one of these things, something called private key encryption. Private key encryption is probably the most important thing in using with cryptography. Means you and me and Elon communicate, and we have shared a key at some point. So we meet in advance, we share a key, and we like to send messages to one another for a long time. Right? This is what you've seen this movie, the Enigma. Well, what was it called? The Imitation Game. The movie about Turing. This is exactly the Germans were communicating with their submarines. They had a key that was established once and for all, and they wanted to communicate for a long time. Okay? Can we get such type of communication? The key here is that the key is much shorter than the message. If you can have a key that's as long as the message, you can do something called one-time path. There is information theoretic security. Very easy. You don't need anything. But if you would like to communicate with a short key and send long messages, you need one-way functions. And if you have one-way functions, you can get it. You can get something that's secure. So secure means can never be broken, except if you do exponential brute force search. So no probabilistic algorithm can break this. Okay. There's something called a pseudo generator, digital signatures. Digital signatures is something we use a lot on the internet. Whenever you go to a website and you go to the New York Times, you know it's actually New York Times. All these things are signed so that you can know that you're talking to the secret message from the right person. Okay. Authentication scheme, again, something we use a lot on the internet today. Something with pseudo functions, commitment scheme, point tossing, lots of very important primitives. All these things turn out to be both necessary and sufficient. So let me emphasize again, necessity means that if there ever exists some private key encryption scheme that's secure, there has to exist some one-way function. Okay? And sufficient means that if you give me a one-way function, like let's say multiplication turns out to be a one-way function, so I can give you an encryption scheme. That's secure. So it's fair to say, and this is not a controversial statement. Whether one-way functions exist is the most important problem in cryptography. Without one-way functions, if we don't have one-way functions, forget about communicating on the internet. Okay, our economy is crashing. That's the way we're communicating today. Now, given that this is the game theory seminar, let me actually give you a few little connections to game theory, very briefly. So there is this bit of work going back to Aumann, François Forges, and Dan Porat, regarding whether you can implement correlated equilibria with chip talk. Anyone is aware of this this questioning? So,
also the young generation.
okay, so the question is the following. We know that Nash equilibria, we have a very nice level of stability. Right? But let's look at the simplest question. Let's say I have one Nash equilibrium that's good for you, one Nash equilibrium that's good for me. Can we mix between them? Can we do a 50-50 between these Nash equilibria and find, there might not exist such a Nash equilibrium. If we have access to a trusted third party that says, you know what, today we're going to play Nash equilibrium 1. Okay, then we're going to do it because our strategies say, whatever he says, I'm going to follow that. And then if I follow it, then you should follow it because it's Nash equilibrium. So if we have a trusted third party, the toss is a random point that allows us to mix between these two Nash equilibria and achieve something that's, more fair. Okay. There's also this more sophisticated notion of polarity equilibrium that's, let me not go into that. This is the easiest to just mix my Nash equilibrium. The question is, this requires having a trusted third party. That's not just something we can do ourselves. So, is there some way that you and I can do this mixing on our own? Okay. Can we implement this random point flipping on our own? Turns out that if you have one-way functions, you can. Okay. Using cheat talks. If we can talk to one another, so if we extend the game to say the game is not just a single shot game where we have action, do an action, but you and I we can talk a little bit beforehand. This talk is cheap. Cheap talk means that eventually we talk, eventually we play the underlying game. And the utilities are what are the underlying game. So can we do it? Turns out, yes.
So this relies on the fact that you talk alternately, you cannot talk simultaneously.
You can do it even simultaneous communication makes it easier.
Yeah, but if it is simultaneously,
that is easy.
You don't need.
Then you do it, simultaneously you can just set up, yeah. But let's say, we talk simultaneously. Yeah, I talk first, you look first. So we can do it, number one, if one-way functions exist, and number two, if we're computationally bounded. If we're bounded to be Polymer time algorithms. So if the strategy is Polymer time, then we can do it. So I can give you a kind of a high-level idea of how this would work. We have actually we do it here. Okay. So all right, let's do the following. I'm going to first do it with an envelope. I'm going to pick a random bit, and I'm going to put this bit into an envelope. Okay? And then I put it on the table, and then I say, now it's up to you guys to say a bit. You pick a bit, right? It's a two-player game. I pick a bit, you pick. But I'm not giving it a bit. So you pick a bit, B prime. And then afterwards, I'm going to open up the envelope. So now I open up the envelope, and I pick out the bit B. And then eventually, we do B plus B prime. And we let B plus B prime be the selected bit. Okay? And what I would argue now is that this actually gives you an unbiased bit. This is what we refer to as coin tossing. Because when you're selecting a bit B prime here, you have no idea what I had here. Right? So if you pick a random bit, then no matter what I picked there, I maybe didn't pick a random bit. I always pick 0. Even if I always pick 0, if you pick a random bit here, then this will be truly random. Right? Okay. So now we know that you don't have to trust me. If you are playing this honestly, you know the bit is going to be random. Now, I also want to make sure that you cannot trick me, right? That flies on the idea that if I pick a random bit, if I put it in the envelope, you don't see what's inside. So no matter what you pick, right? This really is like I'm picking a bit after the fact, right? Because you have no idea what it is, and therefore it's secretly random. So this works if you have envelopes, but envelopes, we don't have, envelope is like the trusted device, because I don't know it's a good envelope. Maybe, I made the envelope and I can look inside, right, I give it to you. Or if I am creating an envelope, maybe I have an envelope that I put in 2 pieces of paper in it, not easy to do this. So we like to do it using cryptography. So how can we do this using a money function? So we give you kind of high level idea that's wrong, but I will tell you why it's wrong, and it's an intuition how to be fixed. So I'm going to instead of bits, let me pick a string R. Like this. And I'm going to let you pick a string R5. And I put it through the money function. Okay. And then eventually I'm going to tell you what R is, and then we can compute R prime plus R. And this will be the answer. So when I write this like O plus like this, that means plus mod 2. Okay, excellent. All right. So I said F bar. This is a one-way function. So it's hard for you to actually recover what R is. Okay. So intuitively, same approach. Like it's like putting it in an envelope, and then I can later open it up by giving what R is, and you can check it's indeed a good pre-match. So does this work? But first, let's look very convincing, right? Perfect. Right? That's problem number 1. If this function is not injective, then this is really like this envelope that I can put 2 things inside it. Right? So maybe I actually have 2 things, so now I can choose the one I prefer, and that will give me the equilibrium I prefer, so I cannot cheat. Okay. All right. So if this is a permutation or injective value function, at least I cannot cheat. Okay. How about can you cheat? Turns out that actually to check some more. A one-way function only guarantees that it's hard to recover all of R. Okay. Maybe I can recover the first bit, right? Or half of the bits. It's just that you can't recover all of it. So you can modify this protocol. You can in fact, what to do here is I'm going to still pick a bit. And what I'm going to do here is I'm going to give you R. Let's assume now that this is a permutation. We know that for you cannot recover all of R. So there must exist something that's hard in R. If I could just squeeze out 1 bit that's hard for you to predict, then we're good. And there's a beautiful result called the Kolmogorov theorem of the Kolmogorov professor Weizmann that shows that if it's hard to predict, if it's hard for you to recover all of R, then if I compute inner product of give you R and inner product of R and S. So this is inner product mod 2. So if I take a random bit string S and I compute the inner product of S and R mod 2, that thing is going to be completely unpredictable. So you can kind of like squeeze out, if there exists something that's hard to compute, then I can squeeze out 1 bit that is actually hard to predict.
The inner product is with XOR and it's with XOR and N.
So this is
So what
this means is I'm computing SI or I mod 2.
yes, but okay, the question is if I can predict all of R but to the first bit R.
Okay, that is not one way.
What?
If you can predict all of R except the first bit, that is not one way because then you can predict all of R from 1/2. Right? So that's why, intuitively, if it's one way, there needs to be at least log n bits that you cannot guess, and therefore Like, really think of it as like, maybe the easiest way to say, that means XOR together everything. XOR together everything, that actually doesn't work because maybe, you don't know this one, but this first bit and last bits are correlated. Anti-correlated, so once you XOR together, they cancel out, and then you're only stuck with the ones that you know. Okay. So that's why you have to, what this does is say, pick a random subset of them and XOR those things together, and that turns out to work. Okay? It's a very beautiful, interesting proof. There's several different proofs. One is using free analysis, one is in more great. It's very nice. If you haven't seen this, it's actually very mathematically clean and beautiful. Okay, so that gives you some connection. This is not important for cryptography. It's also important in game theory. There's several other connections to one function game theory. In mechanism design, it turns out that whether you can get turn efficient algorithms into efficient set-compatible algorithms. Also, if one functions exist, there is a possibility result. So there is a lot of connections actually of one functions in game theory also.
Can I ask one question? So you said in game in computer science, we use the probability time in order to generally say what is usable and what is not. And you said it
not computable, it's efficient.
Efficient.
Yeah.
And we said that using game theory in order to use all these devices, we said that the computing efficiency is bounded. So we use also probability time.
Yeah. So in order to discuss this type of like implementing correlation devices or correlated equilibria, this will only apply in the context of computation fundamentals. Yeah. There are actually some other more confusing results, saying there are several things that are impossible to compute efficiently if players are unbounded. Like finding Nash equilibria, we actually believe it's computationally hard to do. Okay? We can they exist, but we can't find it. Question then is what happens in repeated game? Repeated games, anything is Nash equilibrium. It's so easy to get Nash equilibria. Turns out even in repeated games, it's actually hard. Turns out to be hard to find Nash equilibria. But if players are computationally bounded, using computational assumptions such as multifunction, then you can find them.
But again, in repeated games, it's difficult to find Nash equilibrium.
Yeah, so because you need to have this like punishment, so computing these punishment strategies, so turned out to actually be computationally hard also. Like a two-player thing is easy. In a multiplayer situation, it becomes harder because we need to compute a correlated punishment, correlated minimax, and therefore that is turns out to. But if you allow people to actually communicate securely, which you can establish in cryptography, turns out that you can actually establish this correlation, which is good enough to compute this. You can now compute a correlated punishment instead of independent punishments. And so it's a paper which I helped myself. So if so it's kind of confusing, like if there's a computation bounded, then using cryptography you can actually do things more efficiently. Okay, that was all the connections I wanted to give you. And by now I think you'll be convinced, I hope, that body functions are super important for cryptography, for communicating on the internet, and also in game theory, if you care about computation bounded agents. Okay. This is not all there is in cryptography. There are some more advanced primitives that people have been studying in recent years. So it actually started already in the 80s. There's something called public key encryption that's more advanced. We don't know how to get public key encryption from money functions. Something else called secure computation will be this transfer, which is like very good. And more recent things, something obfuscation. There are more advanced crypto. This is what we call the basic cryptographic tasks.
About zero knowledge proofs.
Zero knowledge actually falls into here. If you have one function, you can get zero knowledge proofs.
Can you elaborate on that?
How to get zero knowledge proofs?
Yeah.
I have to go into defining what zero knowledge is, but actually, to get zero knowledge proofs, it's very similar to this. What you want is a way to implement envelopes, physical envelopes, and that's what we did here. This is a way to get physical envelopes from this. I showed you here now, is commit to one bit. But if you repeat this in parallel, you commit to many bits. This is commitment schemes are the main key thing underlying zero knowledge protocols. Okay. So if you can get this, then you get zero knowledge for all empty. if you want, I can spend some time going over zero knowledge. It's been a little bit of a different topic. It will take me 10 to 20 minutes, but I'm happy to do it again afterwards to go over zero knowledge.
Can I ask a question about multi-party computation?
Multi-party computation, it's more complicated. Multi-party computation turns out that if you, depends on what level of security you want. If you want security, we assume that more than a majority are honest, then you don't need anything. Okay. If you want to assume, if you want to get security, even if any number of people are corrupted, or let's say two-party computation, you need this strong thing called OT. We don't know how to get it from one functions. So this implies money functions, it's stronger than money functions. There's a strong primitive, it's probably one of the second most important questions in cryptography is whether money functions imply public encryption and OT. It's a good question. So, okay. All right, so, but yeah, without money functions, all of like these things die also. Public encryption, OT, secure computation, your knowledge, all these things. And indeed, like when I say advanced, zero knowledge looks like a more advanced primitive, but it turns out to actually falling together. Okay, so the question is, do these money functions exist? So one very basic observation that was made in the by Diffie-Hellman already in 1996 was this NP versus P problem seems to be very related to this. Everybody knows NP versus P? Yes? No? So? Okay, NP is a class of problems that can be solved in non-deterministic polynomial time. So these are the class of problems that if I give you a solution, you can check it that it's correct. Okay? Finding it might be very hard, but I can give you a solution. If I give you a solution, you can check it. And the NP versus P problem is it the case that all problems which you verify solution efficiently, you can also find it efficiently? Obviously, we believe that would be crazy if that was the case, right? That would mean that every theorem that is true, I can find the proof very efficiently. Then we don't really have anything to do here, right? So we believe that NP is not equal to P. Now, the question is, if NP is not equal to P, can we get one functions also? So if you have not observed, if one functions exist, then NP is not inside P, it's also not inside something called PPP. PPP means it can also not be done efficiently with randomness. So BPP is probabilistic all the time. Because we think humans we have randomness, so probabilistic all the time is what we view as efficient computation, right? And why is that? Can somebody tell me? Yes, why is the case that if one functions exist, then NP cannot be inside? It's not equal to P.
Because the witness of the
input. Yeah, exactly. Yeah, there is a very easy input. Is find the pre-image that is that's the witness, and if NP is with P, you can find it. It's very easy to pick one functions. Okay, so we know that this is a stronger thing. Right? So whether one function is a harder question proving NP is not equal to P. So, what's called the holy grail in cryptography is to say that these things are actually equivalent. It would be awesome to say that if NP is not equal to P, then one functions exist. Again, has not been proven. Okay, they're mostly negative results. People try to show that these are actually different, might be hard to prove them. They're all very partial, so we really don't have a good understanding whether we get this. This would be ideal because if this were the case, then we can get a base money functions on this other classical problem we know which is minimal. Okay, but we don't know how to do this. So we don't have this holy grail, and therefore, what should we do? Because we want to use cryptography. We know that money functions are necessary to use all these non-trivial things. So what do? Well, we go back to where we started. Let's go back to some candidates. We start off with one, right? Factor. Multiplication was easy. And we just assume that it's hard to factor. Okay? There's a few others. Going back to Diffie-Hellman, they had this discrete logarithm problem. They said exponentiation is easy, but finding the logarithm, we believe is hard, at least if you work mod P. These are bad. There are various different lattice problems that have been more popular in recent years. And there are some more heuristic constructions that were applied to cryptographers using. Basically, take some function that looks somewhat hard and repeat it many times. So repeat f of f. And maybe f wasn't hard, but if it's not, if f isn't linear, then if I repeat this like sufficiently many times, then it should become pretty hard. Okay, that's kind of the principle behind these things. You have to do it in the correct way, right? Clearly, if it's linear, it doesn't help at all. But if it's non-linear, it makes it seem to be harder and harder. Okay. So we have some candidates. And all is good. So far, none of them broken. Very good. Okay, but for how long? Sorry? Not as a money function, but yeah, let me not go into it. Yes. There are some like
And the whole thing, how many times we iterate?
The test is iterating the things once, but okay, but just because it's short key.
So no, that is, when you have a short key exponential brute force search, I don't want to get into. What I'm talking here about in the limit asymptotic. Okay. It's not broken as a one function. Yeah, it's not, but okay. The point here is that yes, maybe these heuristic ones, okay, that's proof, but like these things have survived. There's this famous quote by Sylvan Kelly from the 80s that cryptographers seldom sleep well at night because we can wake up any morning and maybe someone has factor numbers. And then like, oh, what do we do here? All these like papers, beautiful papers in growth, assuming the Hardness of factoring, they're all now broken, they're pointless, right? Because really cryptography papers are like assuming this conjecture, then we get something else. But if somebody breaks the conjecture, that's all my papers are gone now, right? So that's a horrible state of affairs. I don't think that's the only reason, I think he just has to sleep well. He was my advisor, so maybe cryptographers have this, just more stressed than average, but that's at least a good explanation. And indeed, now there's this other creature that's happening, coming closer, this monster of quantum computers. And if they actually get built, turns out that Peter Shor has this algorithm that does factor numbers and solves this cryptography problem. So if they can actually build a large scale, these things are gone. These things are not gone, but they've been around since '96. Who knows? That's not so long. Some of these schemes in the crypto cycle survived like for 300 years, and today they can be broken like this. So we don't know. Okay, so have we really escaped from this crypto cycle? So what we've done is something very well, not really, but what the field of cryptography has done since Diffie-Hellman is to say, we have these like amazing like houses here, encryption and digital signatures and authentication. All these things, they're not they're not constructed from scratch, but they all are constructed based on one function. Right? So here we have a clear science. This thing is sufficient. If necessary, we get this high level primitives. But the very foundation, this is all standing on a table here, right? If one functions, there is still kind of heuristic nature. They're all based on exploitation, and here we're still kind of in this cat-and-mouse game.
Just a question. If there are quantum computers, so that's your definition of one-way?
We don't know if quantum computer can break one-way functions. Okay? That would be very sad because then we wouldn't be able to use the internet for anything like private, right? Because as I said, one-way functions are necessary for all these things. So the question we're looking at here is, does there exist some natural problem that is kind of complete for cryptography? I'm going to call it kind of like a mother problem. A problem has a property that if this problem is hard, then one-way functions exist. And if one-way functions exist, then this problem is hard. Okay, let's say factoring has a property. We know that if factoring is hard, then one-way functions exist. Fine. But we don't have the other direction. it's not the case that if one functions exist and factoring we know is hard. Right? It could be that there is something else, like a particular quantum computers, right? So that has not been the problem. If we have such another problem, that means that if we had a topic, look, then we should just focus all our attention on that. Let's try to break that. And forget about everything else, let's focus on that. And that will tell us whether we actually have secure encryption or not. So there is a sort of partial solution to this. Leonard Levy defined something called the universal mode function. He showed some problem, a very, very artificial problem, and indeed, even in his paper, he said that this is not meaningful as a problem because it's based on some kind of enumeration, so it's not a natural. The whole point is that we get a natural problem. Now, what does natural mean? Well, natural means that it's studied in its own right, it's interesting in its own right, like factoring, right? It's studied for a while. And so our main result in this paper is actually identifying the first natural problem that characterizes Wally functions. Okay, and that problem is called the T-bounded Kolmogorov complexity problem. Okay, so let me read the statement, and I'm going to go to the final. So we show for the polynomial T, Wally functions exist if and only if T-bounded Kolmogorov complexity is might be whatever. It's going to explain shortly what that is. Okay. This is using computer science notation. I think we'll get to the definition, actually, it's not very scary. Okay. So let me start off by telling you what's Kolmogorov complexity. So now we're switching gears, forget about crypto for a while, and move on to Kolmogorov complexity. Okay. How many of you guys have heard about Kolmogorov complexity before? Okay, so we'll go. Kolmogorov complexity is trying to answer the following question. Here on my slide are two strings. Which one of them is more random? What does it mean for a string to be random? Randomness is a property of distribution, right? Okay, the fact that an individual string be random doesn't mean anything. Okay, but if you look at it, it does mean something like this. It clearly is not random, right? So we say it's 1, 2, 3, 1, 2, 3, 1, 2, 3. Whereas this one I produced by pushing random digits on my keyboard. Okay. So you might say, well, the way you produce this, that would be kind of like a postmodern way of saying defining random. You won't have a mathematical thing. Okay. So how can we mathematically make sense of mean for a string to be random? And this notion of Kolmogorov complexity actually does exactly that. And it's a beautiful notion. It's very simple to define it. So we said that the Kolmogorov complexity of string x is the length of the shortest computer program that generates a string x. Okay, so this program, this string, I can write a short program. It's like 4i = 1 to whatever it is, 50, print 1, 2, 3, and then iterate. Okay. And this thing, I cannot do much better than print this whole thing. So there's one simple observation we like to make here is that the Kolmogorov complexity of a string of length n is never much more than n, because you can always just write print and then string. So it's n plus some constant. We're going to make use of that observation later. Okay.
And I asked the petition how you define the length of the shortest program.
Yeah, now you're right. This is very informal and you need to be tedious and define it. And that's why definitions of Kolmogorov complexity look great when you look like this. But then you have to go into it, you have to define what program is. What programming language? Python, C, Java, which one is it? Okay, so, and of course, when they defined this in the 60s, they didn't even have Python, Java, or this beautiful MacBooks, right? So they define it, you define some computational model, something called universal tool machine, that is tedious to define, right? So mathematically, of course, the definition becomes a little bit uglier because you need to define this notion of computation. So you need to define a computing device. Okay? And then once you've done that, now we're looking at the length of the shortest program, which is equal to this universal computing device that alpha is string x. Okay? So it requires some notion of computability. But it turns out it's not really that relevant whether you do Java, C, because the length is only going to be very slightly different. And now we can say that something is random if it has large Kolmogorov complexity. Kolmogorov complexity close to the length of the string, whereas this one has very small. Okay.
How do you know which program is the shortest?
Which is so, okay, now what you're asking here is like, you know, how do I determine this? Awesome notion, right? Beautiful to say that this is run, this is not. Can I compute it? So this notion, like Kolmogorov complexity, I won't go into it now because I'm only running out of time. Lots of amazing applications. It has, to me, it has the most beautiful proof of galaxy completeness theorem was through Kolmogorov complexity. This was in fact Shatan, what he did. He introduced, so this was introduced independently by Solomonov, Kolmogorov and Shatan. Shatan has this very elegant, much cleaner proof of galaxy completeness theorem. It has some other applications in this pure math, or like the density of primes. It's a beautiful, you know, very simple proof in the density of primes using Kolmogorov complexity. Lots of very nice applications. But we're stuck at this question. You know, it has applications, but if we use it in practice to say, like, hey, which string is more random? Can I actually determine which string is more random? No, we can actually not. This is not computable. And when we say computable here, I don't even mean efficient computable. There is no computer program that can actually compute this. But so it's uncomputable, and this is uncomputability is great when you want to prove a completeness theorem. This is actually what's used to prove a completeness theorem. It's not very good when you want to be like practical. So great question, and in fact, you know, Kolmogorov was aware of this thing, and that's already back then. He said, "Okay, it's great, but in practice, we need to have a better notion." Yeah?
Why isn't it computable if I just run all over the Turing machines possible in the existing side?
Yeah.
And then doing.
You never know if there's you know, there is if you just run this program for a little bit longer, if it's going to, right? You don't know if this program never going to halt, or if it's going to halt, or yes. Eventually, right? So.
Yes.
Okay, so they define this notion of time bounded Kolmogorov complexity to say, like, look, the problem we had before is that the Turing machine can run forever, so it's an issue. So what we should do, which is more meaningful, is to say, let's impose some time bound t. T is some function. Think of t as being, let's say, n squared. Okay, so an input length n, I can run n squared steps, and then after that, I cut you off. No more running. And now we can again ask the same thing. What's the length of the shortest program that outputs this thing within time t? So, you know, I missed a beautiful picture here, Mandelbrot. So why do I have Mandelbrot here? Anyone can guess? So Mandelbrot is kind of a canonical example of something that looks super complicated, right? And if you just take a picture of this, then you require a lot of data to just store it. But it has a very, very short description. So the Kolmogorov complexity of this thing is tiny. Okay, but it looks like it's very complicated. Okay, so now we can ask the question. Once I do this KT, can it be efficiently computed? Okay. And that's a question that was studied in the Soviet Union since the 1960s. And so this is known as the time-bounded Kolmogorov complexity problem. In the Western world, since it was Iron Curtain, which we hope won't happen again, was studied only in the US since the 80s, independently by Euros of Money. We founded the computer science department at Cornell, actually. And this is closely related to some other problems that we call minimal circuit size problem. There is a whole field of something called meta complexity in computer science studying these type of questions. Okay, so this is the problem we're going to look at. So it's quite interesting, actually. This back then in the Soviet Union, I actually learned about this problem in a survey written by a professor from Tel University, Trachtenberg, Boris Trachtenberg. I think it was also with you guys. I don't know. It was in math or so. It was up until a few years ago. So he wrote a survey about what happened in the Soviet Union about these questions. And back then, they believed that this problem could not be solved better than brute force search. Like clearly this thing, if you can run an exponential time, you can just try all possible programs and just run over t of n steps, right? So that will now take 2 to the n times t of n time. Right? So it can be computed, just takes exponential time. And back then, your conjecture, that basically is the best you can do. This is referred to as a parabol conjecture, brute force search conjecture. Therefore, this one is as hard as it gets. So before going back to what the result is, let's just like philosophize a little bit. What does it, why is this problem interesting in its own right? Okay. And I would argue that this problem is really much more deep than most problems that you think of, computational problems. So let's say that you come up with an algorithm that does this. So you break this parabol conjecture, you can actually do it efficiently. Okay, what can we do then? Like if you come up with an algorithm that solves time-bounded Kolmogorov complexity, and let's say you can solve it in a strong way that will give us the to actually find the program. Okay? We can do optimal compression. So whenever we want to take a file, compress it, we can do it. Okay, because we just find the shortest program generates this, and great. Now it compresses the file. Awesome. Okay, so we're saving some money because now we can outsource it to Google. We don't have to store as much. Okay, good, but not that amazing. So I like to argue that there is actually something much deeper going on there. Okay, and please forgive me. This is going to be very non-mathematical now, but at least I want to drive home this point of why this should be important to you guys. I'll take your question shortly. Okay, so okay, so this is not very informal, but please forgive me. So what I would like to argue is, if you can do this, then science is easy also. Okay. So at least if you believe Occam's razor. So what does Occam's razor say? Well, this is what it says, reaching from 10 to 100, and there is a lot to be multiplied without necessity. Okay. So what this means is typically that if you have some phenomena that you've observed, the simplest explanation for that phenomenon is most likely the truest. So what does this mean in our language? Well, you have seen, you've observed some data. If you want to understand why this happened, find the shortest program that generates it, and that's going to be the most likely explanation for why it happened. And then you can continue running that program to generalize what's going to happen later on. So really, if you can do this, then you can, science becomes easy. Okay. Now there is an asterisk because of course, not all science, we're still, where do we get the data from? Right? We still need to get the data and do the observations, so there's still something. But at least, what we think of that the creative part of science, of like finding a model, that is going to be easy. So this problem is really, I would argue, super, super fundamental. Okay. Yes, no, sorry.
And so I don't understand why in one that change is easy, this thing happen, not in the one that change.
Oh, okay. Because typically here, it wouldn't be so interesting to have an explanation of like what happens in the world that is like this requires exponential time to run the model. I would like to have an efficient model that explains the phenomenon. Right? Same thing with compression. It's not so interesting to say like, oh look, there is a compression algorithm that takes 1 billion years. I cannot use it. Right? I want to be able to encrypt, compress my files. I would like to get an explanation for like why does this COVID happen? Okay, how can I predict who's going to get infected? What is the best way to understand that? If that takes 1 billion years, not so interesting. That's one. Yeah, great question. Okay, so right now we talked about what it means, what this problem is. And now I would like to talk about what makes this problem to be hard. So already in the 60s, they back then said, consider what they refer to as the frequential version of this problem. They said, does there exist some efficient algorithm that computes KT for a large fraction of strings? Okay, that's what we in computer science call if something cannot be done for one fraction, it's hard on average. It's hard on random inputs. So if you don't like forget, you're a computer scientist, forget about average. Frequency version maybe makes more sense for you, right? We're just talking about what is the fraction of inputs in which I can do this. And I might not have to do it on all inputs, but can I do it for like 99% of inputs? And they made a simple observation. They said the following: if I don't need to compute it exactly, the Kolmogorov complexity, but if I only need to be within log n, or n is length of the string, then there is a simple algorithm. This I should use the proof. Very simple proof. It's a simple algorithm that does it probability 1 minus 1 over n. And what is that algorithm? It's completely naive. It just says always output n. Right? Always output n, the length of the string. And the length of the string is actually going to be correct. It's going to be n. Sorry, the Kolmogorov complexity will actually be close to n with probability 1 minus 1 over n. So very high probability. Why is that? Okay, because by counting arguments, there are very few strings that have Kolmogorov complexity that's smaller than n minus log n, right? If you think of strings of the Kolmogorov complexity n over 2, there are only 2 to the n over 2 to the n over 2 such strings. So there are very few strings that have Kolmogorov complexity less than n over 2. So if you pick a random one, it's actually going to be high. This is only small things that take it up. So if you don't need to be exactly right, but only approximately right, well, there's a simple thing you do. Question is, can you do better than this? And that's what they're asking. Here's a naive algorithm. Can you do better? Right? Can I, or even can I just handle a larger fraction? Let's say I want to be within log n. And actually, there is a good reason to say being within log n is good enough, because anyone want to guess why people like this approximate notions? Because if we use Python, Java, there will be small differences. Okay, but all these differences will be within log n. So people like this approximate notion. Another question: can you beat this bound? And so that is what we're going to say. If something is hard on average, if you cannot do better, mildly hard on average, you cannot do better 1 minus 1 over n. Okay. So you can define mild on average to compute exactly, and mild on average approximate. And we're actually now ready to state the theorem. Time. So the theorem is the following: one-way functions exist if and only if the following things pre-exist at Kolmogorov, such that KT is mildly on average to compute exactly, and in fact, also it's mildly on average to approximate. So basically, if you can beat this bound that they consider in the 60s, the naive algorithm, then you can actually break all one-way functions and forget about cryptography. Okay? And if cryptography exists, then this bound is roughly tight. So there are this statement, there are two corollaries here. The first one is what I kind of care about as a cryptographer, which was this one-way functions exist if only if KT is on average. Cannot be, sorry, it's just a KT cannot be computed with high probability. Let's say that for you guys. Okay. Okay. But the second corollary is these two things are equivalent. Okay, the hard on average, computing exactly, computing approximately are equivalent. That talks nothing about cryptography, but it's a quite interesting statement that has been open since the 60s. So whether is it easier to compute something exactly than computing it approximately? Sorry, is it easier to compute something approximately than computing it exactly? So out of this thing, we actually get the equivalence of the two popping out. And so computing something approximately is as hard as computing it exactly if you don't do it on average with high probability. The surprising aspect of this thing is actually this uses, like this really, the way this is proven, if you're showing one-way functions, if it's hard to compute exactly, we get a one-way function. If one-way functions exist, we show you can get that it's hard to compute approximately. And this uses, I won't go into detail, but it uses a lot of techniques developed in the field of cryptography for the last 4 decades to go from here to here. This thing is actually easy, relatively easy step. It's a direct proof, but here you use a lot of cryptography material. As we take it together, it gets this resolution to this problem, pure Kolmogorov complexity. Question of like, is it easy to approximate or compute exactly using these cryptographic tools? Not clear at all how to do it without it. And it's kind of surprising that particularly it uses this type of like Levin theorem that it's just here. That's an integral part of doing this. So I don't have that 10 more minutes. I don't know. I can go into some of the details now. I don't know how you do this or maybe just take more questions on that.
Yeah. What's the special feature of Kolmogorov complexity that makes 2 and 3 equivalent?
So that's the surprising aspect. Not clear how to, going from 2 to 3. We don't know how to do a direct proof. The way our proof goes here is really like from here to one-way functions, and then we're using cryptographic machinery. In particular, if you have a one-way function, you can get something called pseudo-round generator. Okay, these are some of the fundamental results actually in cryptography. For one-way function, you can get something called pseudo-round generator. In fact, let me try to give a high-level idea of this stuff. Okay. So. So a pseudo-round generator is a function that takes a short seed and outputs a long string. Okay. And what I want from this long string is this long string looks indistinguishable from a true random string. It's not random because it can be generated by something short. Right? It's expanded from something short, but it looks like a random string. So what I mean by looks like, it means that no efficient algorithm can tell apart when you get a sample of a truly random string of length 2n and something from output for PhD. PhDs are actually the key tool we need in order to get secure encryption on the internet. Because roughly speaking, what you do is you take your key, which is short, and you expand it to a long string, and then you can add this long string to your message. You can use a one-time pattern. So PhDs, if you have a PhD, you can do it. Now, how do we get a PhD from one functions? Very, very complicated. This thing that I just showed here of using this hardcore bit, using inner product, is step 0.5. Okay, and then there's a lot of work. Okay, and beautiful and very sophisticated machinery to do it. But let me try to give a high-level idea of what PhDs. If you have a PhD, so from one-way functions, you can get a PhD. If you can get a PhD, how can you now show that Kolmogorov complexity is hard to approximate? And here's the idea. Random strings, as we argued already, have high Kolmogorov complexity. Right? With high probability, the Kolmogorov complexity of a random string is more than a string of length 2n is 2n minus log n with high probability. Okay. If I sample something in the range of the PhD, the Kolmogorov complexity will always be small. Okay, how small? The length of the seed plus something constant, which is the length of the program computes a PhD. Okay, so random strings and pseudo-random strings. If you can decide KT, right, then you can tell us these things apart. So this, and here the gap between these things is very big. It's actually between n and 2n. It's really huge. So even if you can approximate within like log n or much more, like here it seems like you can approximate within n over 2. So you get a huge gap. Okay. That's it, more or less. Now this unfortunately doesn't work. This works if you can compute KT probably to 1. But that's not what I could show. Like what we needed was that it's hard to compute with high probability. So let's say I have an oracle, they only can compute KT with 99% probability, I'm not going to find. That's not going to be good enough for me. Like here, the KT oracle is going to work nice. Okay, because here at random strings, it will work with 99% probability. If I run it on pseudo strings, it can just give me the wrong answer always. Because they are much smaller than 1% of the strings. They're tiny, tiny probability match of these things. So this algorithm might just give the wrong answer. Okay, so this doesn't quite work, and what we do in our paper, we define a more sophisticated creature of a pseudo generator, something called entropy preserving PhD, which is something where now things become a little bit more messy. It is something that's pseudo-random. The output is pseudo-random, but I also require that the output of the pseudo generator has high Shannon entropy. Why does this help? This requires some details to prove, but the idea here is that if the output is high Shannon entropy,
Shannon would be in sense of frequency of bits or words. Well,
in the bits, yeah, the whole string has high entropy. Okay. If this isn't clear, because I'm not ready to prove here now, I have it, but I'm trying not to do it here. But on a high level, like the idea here is that I want to make sure that these strings are not too sparse. They need to be dense enough. Okay, so that if I have an algorithm that works with 99% probability, it should also work with decent probability on these strings. And then I can use that to tell apart if I'm here or here. So I need something where this actually is not too sparse. And it turns out that if you look at the right notion entropy, that is going to be enough to make sure the algorithm works there. Okay. So we need to have this PhD that is kind of like, on the one hand, it is expanding, but it's not going to expand too much. It needs to make sure that it still has enough randomness here. Then it's a more delicate creature. You can set the parameters right to do that, and you can provide a construction such a thing. And that's what we do. So.
Thank you very much.
For example, almost. Any questions? I can express your knowledge there if you want afterwards. I'm sorry if this was far away from games theory.
Yeah,
this is
connected it.
I know. That's what I said. I could have talked about games theory also.
Okay, so thank you very much.
thank you.
My friend, so if I would go to the essence of the word here, that Kolmogorov complexity has this one way function idea that you maybe have a short program that generates that it would be hard for you.
Yeah, exactly. So basically, this one we show that this is kind of like a this one function of this is kind of complete. If this gives you some kind of candidate-value function, I didn't show you how to get a candidate-value function. Actually, it's actually the candidate-value function is or the one function you get from this program is actually very, very nice and easy also. So this is the one function. It's actually very simple one function, not as simple as multiplication, but it's a very simple one function. So if you have a minute, I can explain what the function is. So the function is the following. I take an input. Okay? I'm going to interpret my input as consisting of a. I'll do it here. So I take my input. It consists of some long bit of strings here that we call this. This is n bits, and this is log n bits. I'm going to refer to this as an index I, and this as a program regulator pi prime. Okay. The first n bits, I call it pi prime. These are just n bits, and this is an index. What I will do is I'll take this and I chop it off at the ith bit. So we're going to let pi be the chopped off. This is the first I bits. So this is now pi chopped off from 1 to bit I. So take it, chop it off, and now interpret this as a program and run pi for T of n steps. So take it, run the program. Okay. Remember, our theory was for any t that's greater than 1.1 n. So this is a very efficient. It's linear time. Run it for 1.1 n steps, and this will eventually output some string y. And then you're going to output the index and y. And that's your function. And I'm claiming that if you can invert this function, then you can actually compute kt with high probability. And on a high level, the idea of why it should work is easy. Because give me some string y, like let's say you give me a string y, and I would like you ask me, what is Kolmogorov complexity string? Okay? What I will do is I'll take y and 1, ask, is there some program, like putting in y and 1 here, I'm asking, is there some program length 1 that's going to generate a string? Because that's what it needs to invert it. It needs to find something here that if you chop it off at length 1, it will output string y. And then run y and 2, 1 and 3, and you output the first one that works. Okay?
That's correct. Thank you very much.
So intuitively, this should just work. And indeed, if I have someone who inverts it probably to 1, this trivial method works. And the whole problem is I don't have an attack that works probably to 1. I have something that works with only some, let's say 20% probability, then running travel because it's more complicated otherwise. But yes, the essence here is really like Kolmogorov complexity has the property that if this property is hard, crypto is hard. We can do secure crypto. If you can break this problem, bye to crypto. At least these things. There are still some intriguing, some information theory cryptography possible. Like MPC, you can do it if you have more than if you assume an honest majority or 2/3 honest and so on. If you want to do things, two-party things, then mostly
So does your thesis advisor has sleeps better or worse?
he has a company now, so I think he sleeps even worse. With money, that is.
Okay, so thank you very much.
Thank you.